Rightio, so this is the second type, okay, where you have got not the homogeneous type where it equals 0, but you're possibly going to have some function of x, okay, and you've got to make allowances for this this situation. So the reason why you can add the solutions up at the end is something to do with it being linear, and they're all independent solutions. Okay, not dependent solutions, they're independent. What that means, I don't know. I just looked up the words and that's what it meant. So you add them. So anyway, here we go. So when you're given the function of this again, in this type, okay, and you've got some function of x, this is linear because these are all constants, okay, constants here. And you've got d2y, dy and y, all with respect to x. And you've got a function here. So it's a linear, non-homogeneous or homogeneous solution. Differential equation. Okay. If it equals 0 like this, we call it homogeneous, and it's linear because you've got a, b, and c. If you've got another variable here like x squared, and it's all to do with y's, then you can't do it. You've got it's out of this remit. It's way down to university level. Okay, so complementary function. So right, you need to find a solution for this where f of x will have one of the forms. So this will be a function of an exponential function, a linear function, a quadratic function, or a complex function. Okay, or sorry, not complex, but a trig function. You find this by using an appropriate substitution and then comparing coefficients. The solution is called the particular integral. So the first bit you set equal to 0 and you call it the complementary function, and that's what we've done before. And the next bit you try certain functions. That's what you do. Okay, and this is the process. So nice and easy. Right, find a particular integral of the differential equation of this. Right, they've broken it down. Okay, so you would first of all normally go ahead and don't write this down. You'd find the complementary function as you did yesterday or last lesson, and then you'd find the particular integral, and then you would add the two results up. All this question is breaking it down to actually find the particular integral. Okay, so particular integral. Right, everyone happy with that? So this is the second process when you're trying to solve this overall and get the general solution. We're just asked to find a particular integral. So what we're saying is that we're going to try the function. So y is equal to a constant. So lambda. Okay, everyone happy with that? That's the process. So if it's a constant number here, you just try lambda. Y is lambda. You go ahead and differentiate it to set up your differential equation with substitution. So you're going to try y dash. Okay, y dash is equal to 0. Y dash dash is equal to 0. Shove all of this into here, you end up with 0 minus 5 lots of 0 plus 6 lots of lambda, and that is equal to the function of x, and our function of x happens to be 3. Okay, so you end up with basically lambda is equal to a half. So the particular integral is going to be y equals a half. Okay, it's easy as that. Right, so that's part A. We're going to find the particular integral this time if the function of x here is equal to 2x. Now when it's equal to 2x, that means it's linear, but you could have a constant before it. So we have to be aware that we try y is equal to mu plus lambda x. That's what we try. So we go ahead and differentiate it. Y dash is equal to lambda, and y dash dash is equal to 0. And you just put it back into the equation. Y dash dash, well that's 0, minus 5 lots of y dash, which is lambda, plus 6 lots of mu plus lambda x. Okay, and that is equal to the function of x, which on this occasion they've said is going to be equal to 2x. So working this out, you can see that the constant bit is 6 mu minus 5 lambda is the constant bit, plus the x bit is going to be 6 lambda x, okay, is equal to 2x. Okay? Right, what do I know that this must equal? 0, because there's no constant bit here. So the first of my sim equations, if I'm going to need them, and I won't need them for this probably, but generally, you know, as it gets harder, you will. So 6 mu plus 5, sorry, minus 5 lambda is equal to 0, and that brings the second one, which is 6 lambda is equal to 2, and therefore lambda must equal a third. But you need to see if there is a constant. So we shove this in to there to see if there is a constant, and it looks like there's going to be. So you end up with 6 mu minus 5 lots of lambda, so that's minus 5 thirds, is equal to 0. I would work underneath, but I can't, I've run out of space. So I've got mu is equal to 5 over 3 divided by 6 gives you 5 over 18. So therefore, the particular integral is y is equal to mu, so this is what we're putting it back into, mu, which is 5/18, plus lambda x, plus a third x. So that there is the particular integral that you'd have to add to the complementary function to get the general solution. Okay.
So that's just what you put in place of the 6y.
Well, I'll show you how we add it. So the next question, I believe, is how how it's truly used to actually work out what the general solution is. Right, is there space over the page?
Yeah.
Yes, there is. Right. Okay, let's go back to this one. And the particular is this 3x squared. So 3x squared. So if I go on to C, if it's 3x squared, that means it could be quadratic. So I have to try the most basic quadratic, which is a plus bx plus c squared. Cx squared. Okay, differentiate it. Gives you y dash is equal to b plus 2cx, and differentiate it a second time, and you end up with 2c. Okay, and the equation was d2y by dx squared, so it's just one of this, so therefore it becomes 2c minus 5 lots of y dash, which is b plus 2cx, plus, and it was 6y, so plus 6 lots of your a plus bx plus your cx squared, and that must equal 3x squared, is it? 3, let's get across there, 3x squared. So I'm going to expand this out to get my constants. Now my constant is going to be 2c minus 5b plus 6a. So can you see I've got a bit here, I've got a bit here, and a bit there. That's going to be constant. Okay, so I can either see, with speed you can set that equal to 0 because there's no constant. But I'm going to finish this off. We've got add it to the x bits. Well, the x bits is that times that. That's going to give you minus 10cx. X bit from here is going to be that times that, which is positive 6bx. And in fact, I can just pull an x out and just say that's my x's. Okay, plus, and the only squares I get is from there is 6cx squared, and that equals 3x squared. So my simultaneous equations are 2c minus 5b plus 6a is equal to 0. My 6b minus 10c is equal to 0. And my 6c is equal to 3. So I'll work backwards through here because it's the obvious one to start with, just here. C is equal to a half. Okay, I can now use that for this equation just here. So I've got a half of that is 5, throw it over, and then with b is equal to 5 divided by 6, 5/6. And then finally, you can use it for this bit here, which is 2 lots of c, which is 1, minus 5 lots of b, well that's going to be 25 over 6, plus 6 lots of A is equal to 0. Get this over 6, that's the same as saying 6 sixths, which gives you minus 19 over 6, comes over, so 6A is equal to 19 over 6. Divide by 6, so A is equal to 19 over 36, which won't cancel. So I can see that the particular integral will be y is equal to 19 over 36, because you're just putting it back into here, plus b, which is 5 over 6x, plus c, which is a half x squared. Okay, and that's the particular integral for that one there. Okay, so if it's ever quadratic, if the f of x is ever quadratic, you try the general quadratic. Right, and that brings us on to the last, no, two more. We've got d, which is e to the x. Okay, so scrolling down, d, so when it equals e to the x, we have to try lambda e to the x. So what we tried there is y equals lambda e to the x. Okay, so differentiate it as normal. Y dash is equal to lambda e to the x, and y dash dash is again lambda e to the x. So you've got lambda e to the x, because that's dy by the x, minus 5 lots of, sorry, d2y by the x squared, and then minus 5 lots of dy by the x, which is going to be minus 5 lambda e to the x, plus 6 lots of y, which is 6 lambda e to the x, and that is equal to e to the x. Okay, so equal to the function itself. Right, so you can see by comparing coefficients that I've got lambda, I've got 7 lambda, so I've got 2 lambda is equal to 1. So just comparing coefficients, the coefficient here is 1. So lambda has to have the value a half. And therefore, the particular integral is y is equal to a half e to the x. Okay? Half e to the x. Right, and that brings us on to the last one, which is e. And that says that you've got 13 f of x, so I suppose I want to put up here, f of x was e to the x. This time when the f of x is equal to something like 13 sin of 3x. Well, what you have to try here is the complex bit. So if you've got sin, if you've got just a single cos, or if you've got combinations of sins and coses, you still always use this format. So we're going to try y equals, and this can change. So in the normal complex format, we're going to say lambda, lots of cos, and obviously the angle or the argument's got to stay the same, so 3x, otherwise you couldn't compare it, plus mu, lots of sin, same argument, 3x. And again you differentiate this, so you get y dash is equal to, and this turns into a negative, you got 3 lambda sin 3x, and this, well, that becomes still a positive 3 mu cos 3x, and y dash dash, well, that's going to become minus 9 lambda cos 3x, and this is going to swing to a negative 9 mu sin 3x. Okay, so there is a, once you get good at this, there's a quicker way of doing this, but I'm going to do it the long way and leave it for you to find find what works for you best. So here we go. We've got one of this. So I've got, we're out of space there. So one of that, slip it in here. We've got minus 9 lambda cos 3x minus 9 mu sin of 3x minus 5 lots of this. Well, minus 5 lots of that gives you positive 15 lambda sin 3x, and minus 5 times that is minus 15 mu cos 3x, and then positive 6 times all of this, so positive 6 lambda cos 3x plus 6 mu sine 3x, and that is equal to, I can't fit it in there, so 13 sine 3x, okay? So that is equal to the function of x in our second order differential equation. So I can see there's no cos x's, so I can see that anything with cos x, okay, which is here, cos x is here, and as there's none of them, I can see that all of those must equal 0. Okay, I've run out of space, so I'm going to have to kind of fit it in here. So I can see that minus 9 lambda, so I'm just using the coefficients here, I'm not worrying about the cos 3x now, just comparing that, minus 15 mu, okay, this bit here, plus 6 lambda. Well, for that not to exist, that must equal 0. Neaten that up, and I end up with minus 3, okay, so minus 3 lambda minus 15 mu is equal to 0. I'm going to divide through by minus 3, so that's going to give you a positive 1 and positive 5 mu is equal to that. So that's my first and my sim equations. Okay, now I do know that the coefficient here of the sins must be 13, so I can see that minus 9 mu plus 15 lambda, and a bit here is positive 6 mu right at the end, must equal 13. So my second sim equation is going to boil down to minus 3 mu plus 15 lambda is equal to 13. I'm going to divide through by, well, it doesn't matter, you can either times this by, it doesn't matter. I was going to divide through by 3, but it doesn't matter. Right. Okay, I'm going to have to rub out some stuff here now, only because I've run out of space. So all I'm left to do now is solve those simultaneous equations, and I'm left with this bit here, which is going to be times this by 3, so you end up with 3 lambda, for instance, plus 15 mu is equal to 0, and you're going to take it away. Oh, so you're just going to add them. No, I've got the wrong way around, haven't I? Yes, I've got the wrong way around. Okay, not to worry. Take that back. I'm going to times this by 15 to give you 15 lambda plus, and that's going to give you, what's that? 50, 50, 50, 75 mu is equal to 0. And turning this round, I've got 15 mu minus 3, sorry, lambda minus 3 mu equals 13. And I'm going to take top, take bottom, gives you basically 78 mu is equal to top, take bottom is minus 13. Just be careful of your signs. Mu is equal to minus 13 over 78. And I think that's going to cancel, I think it's 6. Yeah. So it cancels down to mu is equal to minus 1 over 6. Okay. So I'm going to shove that into this one here, would be easiest. Okay, so therefore lambda is equal to minus 5 over 6 thrown over gives you 5 over 6. Okay, so straight off I can say therefore, and I rubbed it out here, but up here my statement was that y was equal to lambda cos, so it's 5 over 6 cos 3x, and it's plus, but it's minus there, so it's minus 1/6 sin 3x. Okay, so that is the particular integral for that second order differential equation. Well, what it says here is that you can find the general solution now of the differential equation where a linear, okay, so a number, lots of that, a number, lots of that, and a number, lots of y's. That's why it's called a linear. Non-homogeneous, because it doesn't equal homogeneous, it doesn't equal 0. Okay, that's homogeneous. If it equals f of x, then you have to use all of these techniques here, and you have to try, you know, standard function as I've just shown you for whatever form f of x takes. What you do is you set that equal to 0, forget that exists, go ahead and solve that like you did yesterday to find the complementary function, the CF. You just do the process I've just shown you to find out the f of x, and that's the particular integral, and you just add them together. Okay, so here we go. It says, find the general solution to this. Well, we now need to find the complementary function, as I've just said. The complementary function to this is, well, are you happy with, well, I'll write it down, d2y by dx squared minus 5 lots of dy by dx and plus 6y, and the complementary function is the one where you put it equal to 0. Okay, so it's the homogeneous format that we look at, and we find the auxiliary equation, the augs eq, which is going to be m squared minus 5m plus 6 is equal to 0. We're going to factorise, bing bing bang bang equals 0, m, and I think that's going to be 3 and 2, and they're both minus. So m is 2, m is 3. They're real and different, and because they're real and different, the solution so far for that homogeneous solution is y equals a e to the 2x plus b e to the 3x. Okay, now all we have to do is go back to find the general solution for part A, and we do the complementary function plus the particular integral. Complementary function is always going to be that, so that's fixed for all of these now. That is the answer for all of these. So all I've got to do is go back through what you've just seen and add the attachment. Okay, so part A, it's going to lead to y is equal to a e to the 2x plus b e to the 3x, and I can't remember what it was for that. What was it for a? So plus a half. That's the general solution. That is the general solution for that. And further questions later on in this chapter, they'll give us boundary conditions to find A and B. So that you know Y and blah 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 to find out the particular solution. Right. B. Again, complementary function plus the particular integral gives us y is equal to a e to the 2x plus b e to the 3x, and when I use that as the f of x, what did it give us then?
X over 3 plus 5 over 18.
So plus 5 over 18 plus x over 3?
Yeah.
Okay, so that'll be the general solution there. For C, again, it'll be y equals a e to the 2x plus b e to the 3x, and that was when I used 3x squared for C, and that boiled down to plus
19 over 36.
Yep.
Plus 5 over 6x.
Yep.
Plus half x squared.
So half x squared. That's the general solution for that one there. Nearly there. We've got D. And that again is going to be y equals a e to the 2x plus b e to the 3x. And the attachment for that, when it is e to the x, was that half, I think? Half it, yeah. So plus a half e to the x. That's the general solution for that one there. And I'm going to have to slot in e just above here, okay? And that is going to be, again, y equals a e to the 2x plus b e to the 3x plus, and I've just done this but I've rubbed it out, what was the attachment now? 5 over 6 cos 3x minus 1 over 6 sine 3x. Okay, so those are your 5 general solutions given different f of x's. Okay, so you can see that the complementary function stays the same because all you're solving is the homogeneous solution where it equals 0, the simple solution. Okay, so next one, scrolling down, Right, example 10. Find the general solution to this. So now we can go the whole hog and do the full question. So the general solution to this. So you first have write down in the margin CF, complementary function. You then got to work out the, just to remind yourself for your notes, I mean I'd go straight to the auxiliary equation here, but for your notes you're going to solve the homogeneous solution d2y by dx squared minus 5dy by dx plus 6y is equal to 0. And the auxiliary augs eq will be m squared minus 5m plus 6 is equal to 0. And the reason that's such is because you're trying y equals a e to the mx, remember, okay? That's what we're doing here. Right, so go ahead and factorise that. Bang, bang, bing, bing is equal to 0. M, and this one again is going to be minus 3 minus 2, isn't it? So m is 2, m is 3, and you can see straight off that so far we've got y is equal to a e to the 2x plus b e to the 3x. So that's what we got so far, and all I've got to do to that is find out a particular integral. Okay, so down here, particular integral. Now the reason they've asked this, okay, the reason they've asked this is because they've set the f of x is equal to e to the 2x. And you have already got solutions for that here, so you can't go ahead. You can't go ahead and try y equals lambda e to the 2x. If you've got solutions already, okay, when you're going to come across the next couple of examples like this, if you've got the solution already within the general solution, because in the complementary function, you're not going to get any more solutions because it's already eaten up by this a. So you have to try, for this to exist, you have to try x times it. Okay, so that's the one you try if you've got the same. So be aware that if you've got the same one in there, then you try lambda x e to the 2x. Okay, so you go ahead and differentiate that now. With respect to x, you get y dash is equal to, it's a product, differentiate the first, lambda e to the 2x, leave the second, plus, leave the first, and times by the differential there. Well, that's going to give you 2 lambda x e to the 2x. Differentiate again, y dash dash, well that's just going to give you 2 lambda e to the 2x. And this one, product again, is going to give you, differentiate the first, is going to give you 2 lambda e to the 2x, plus, leave this, differentiate that, it's going to give you 4 lambda x e to the 2x. Okay, right, put them back into the original equation. Well, there's the original equation again. So I've got this, which is going to be 4 lambda e to the x plus 4 lambda x e to the 2x. Sorry, that should be 2x there. Okay, minus 5 lots of this here. So it's minus 5 lambda e to the 2x minus 10 lambda x e to the 2x plus 6 lots of this. So plus 6 lots of lambda x e to the 2x. Okay, and we're comparing that with the complementary function, which is e to the 2x. E to the 2x. So let's gather these up. I've got 4 lambdas here, so I'm just going to highlight this. Okay, normal of those, and I've got normal of those just here. I've got normal, in fact that's it. So I end up with minus lambda e to the 2x, and combining this here, I've got 4, add that, take that is gone. So I've got, therefore, this is equal to e to the 2x. So you can clearly see that lambda has to be minus 1. lambda's minus 1. So I've run out of space on the bottom here again. I would never contemplate. You should always work underneath. I'm going to squeeze it in up here. So therefore the general solution is now, because the particular integral I suppose you can put here, particular integral is implying that it is y is equal to minus 1 x e to the 2x. So minus x e to the 2x is the particular integral. And all you do is go ahead and add the particular integral to the complementary function to get your solution. So the solution is y, or the general solution is y equals a e to the 2x plus b e to the 3x minus x e to the 2x. Okay, and that's the general solution just there. Okay, over the page. My God, there's another example. I've still got some tape on here. How long did you say you got, Brad?
It's still recording.
It'll be
Yeah.
like 20 minutes more.
Okay, right, general solution to this. Okay, so here we go. You wouldn't throw this over because it doesn't contain y's. Okay, so you've got d2y's, dy's and y's, but there's no y's. So we're going to go ahead in here, and this is what you do. Complementary function. So we're going to solve where d2y by dx squared minus 2dy by dx equals 0, the homogeneous solution. Your orgs, eq, is m squared minus 2m is equal to 0, and therefore m brackets m minus 2 is equal to 0. M is 0 or m is 2. 2 real and different, so you know that you've got a situation where therefore y equals a e to the 0x plus b e to the 2x. That's just going to give you, that's going to give you 0, so 0 is there, gives you 1. Okay, so it gives you y is equal to a plus b e to the 2x. That's the particular, sorry, that's the complementary function. Right, so now you've got the particular integral, okay, and that's, we're going to try, if it's 3, what do you try if it's 3? Just lambda. So we're going to try for when f of x is equal to 3, we're going to try y equals lambda. Differentiate it, well y dash is 0 and y dash dash is also 0. So you end up with basically 0. Stop. No one tells me this. What have I just said?
I don't know.
It's constant. The constant, he's already got the solution for a constant, so you can't try it. You've got to not add an x, but you need to times through by an x. So you've got to try that. Not there, sorry. There. Lambda x. My mistake. Right. Differentiate gives you lambda. Yes.
Why couldn't it be like lambda x plus mu?
There's no reason. Yeah, you are right. Sorry. Put mu into it. Okay. So we get that. Differentiate gives you lambda, gives you 0. Okay. So put it into the differential equation. You end up with 0 minus 2 lots of lambda, and that is equal to 3. Okay. So you can clearly see that the mu didn't have an effect here, and it never does. But there's nothing wrong with trying it so that you don't have to question it in the exam. Right, so you've got lambda equals minus 3 over 2. Okay, so lambda equals minus 3 over 2. So the particular integral is y equals, and you go back to what you've tried. Okay, so you go back to what you tried, you got basically minus 3 over 2x is the particular integral. Add them together, and you end up with the general solution is y is equal to a plus b e to the 2x minus 3 over 2x, and that there is the general solution that we need. Okay, right, and about time. Okay, I will leave you with that.